I'm gonna start a new series about waves and sound waves, and this video will be short. So as usual, you can stop the video here and try to answer this question. So here it's about resonance, right? So you have for any object vibrating, an object that can vibrate, right, or oscillate. So like a tuning fork here, and here you have a swing. So if you excite that object at the right frequency, so it's called forced oscillation. So you force it to vibrate, and if the frequency is just right, okay, for this mode of oscillation, it's called the resonant frequency. So if you keep exciting the system, it will go, the amplitude will increase, right? And you can do that with music instruments. So if you excite that tuning fork at the right frequency, it will start to vibrate at a higher and higher amplitude. And you can even excite another one if this one has the same resonant frequency than that one. So you have different modes. So anyway, let's go back. So I have a playlist about that. It's called Waves and Sound, I think, and I go over resonance. But let's go back to the question here. So you have, with those questions, you have to read very, very carefully, because if you don't, you're going to skip that important information. It says that the singer has two perfectly identical wine glasses, which means we expect the same resonant frequency. So the first glass, the resonance frequency is 720 Hertz. So if use the other glass, which is identical, and the frequency of her voice, the pitch is 760 Hertz, that will not be the resonant frequency, so it will not break. Okay, you can have a second mode, but usually they are not that close, right? So the second mode, so the second resonant frequency, higher pitch will be maybe in 1,000 Hertz, not that close. So the best question will be not shatter, because it's not the natural frequency of the glass. So if you want to learn more about resonance, you have this, you have videos that shows you, okay, when you reach the resonant frequency, the glass will break, okay, and different glasses don't have the same resonance frequency. Okay, so let's go to the next one here. So here it's about standing wave. So again, I have a playlist about that, but any music instrument has resonant frequency with different modes, right? So we call that, let's see if I have a slide. Okay, so these are called harmonics, and let's skip to slide 20, 21 or 19. So for example, you have the flute and you have the clarinet. So that will be a flute here, that will be a clarinet. So you see how the air will vibrate inside, making standing waves, right? So it's the mode at which the air will vibrate inside. So here you have one end which is closed, and here you have the two ends open. So that will be a flute, and that will be clarinet, and what you have inside are called standing waves. So I'm not going to go over. You see, so that will be for a string. Okay, you also have standing waves, so that will be the fundamental, the pitch, that when you listen to music, you're gonna hear that. That's the one you're gonna hear. And then the next standing wave will be twice the frequency. Okay, so now you can fit all wave, so that will be half of the wave. Here you have a wave, so that will be a second harmonic, and that will be the third harmonic. So when you're listening to music, it will be you have to combine many harmonics together for one pitch, one frequency. So anyway, I'm not going to take a tangent, but let's go back. So in the mcat, they like those examples here. Open at both ends or one is closed. So let's go back to the question because I forgot what was the question. So open pipe, so that will be a flute. And then you close one end. So what's going to happen? So you go back here. You have let's say you have a flute here, and now you close one end. Okay. So what you can see here is that here you can fit 1, 2, 3, 4, 5, 6. So 6, 4. So 3/2 waves, and here it's going to be 5/4 waves. So you see that pitch here will be higher than this one. Okay, higher frequency, it means more wavelength. Lower frequency means less wavelength. So here you have 5/4 waves or 5/4 wavelength, and here you have 1 wavelength and a half. So this one will have a higher pitch. So the flute will have a higher pitch here for the same harmonics number than this one. So the pitch, you expect the pitch to be lower, right? And so the answer will be, let's look, the pitch of the sound will go down. So it's a lower pitch. You also have equation. You don't have to memorize the equation. You can draw and find the equations. But so here you have a 3D. So this show you what's going on. So high pressure, low pressure, high pressure for the air. And here you have the equation. Let's see, I have both equations at the same time. So here it will be the equation when you have open. So n can be equals to 1, 2, 3, 4, right? So n equals 1 will be the first harmonic or the fundamental. And then here you have the equation when it's closed at one end. So n equals 1 or 3 or 5. So it will be odd numbers. So anyway, let's we answer that. So the pitch will be, the pitch of the sound will go down. Okay, so here they want you to know the equation. They want you to know the equation between the frequency and what we call the angular frequency. So by definition, and of course you can, so the frequency, okay, is multiplied by the wavelength. It's going to be the speed of the wave. Okay, the frequency is 1 over the period of the wave. So frequency, you can say it's the number of revolution per second. The angular frequency, the unit, so the unit for angular frequency, it's going to be rad per second. And 1 revolution is 2 pi rad. So it's like you go from one unit to the other one. Okay? So that means that the frequency, or rather the angular frequency, okay, so rad per second, okay, so it's a number of revolution in rad. All you have to do is multiply by 2 pi. Okay, because that will be revolution per second. So, and then that will be in rad. So omega will be rad per second, and again 1, 2 pi rad. So going around the circle is just one revolution, right? So if you look at the trigonometric circle, you go one revolution, so one revolution, one cycle is 2 pi rad. So let's look at the answer. So this is very basic. And so the answer will be the product, so the omega angular frequency and the period. Necessarily true. Angular frequency and the period is 2 pi. So no, so it should be D, right? So we have, let's go back to here. So omega is 2 pi over T, right? So rad per second, and the frequency is 1 over T. So omega times T equals 2 pi. I didn't look at the answer before, so the answer will be the product of the angular frequency and the period is 2 pi. So here it's important for medicine, of course, to understand ultrasound. So ultrasound is sound waves, and the sound waves bounce off. So it's based on reflection. Okay, so you can have so you have different properties of wave. It can be refracted, it can be reflected, and it can be diffracted. So reflection, for example, here you have application of sound in medicine. So the waves reflect from the baby, for example, and we know the time it takes to go back. We know the speed, so we know the distance, and the computer can make an image. Okay, so the answer will be the time it takes for the reflected sound wave to return. Oh yes, because they want to find a distance. So wave is distance divided by time, so B has to be the answer. So this one is based on the understanding and maybe the equations of the Doppler effect. So what's the Doppler effect? Again, you can go back to my playlist about Doppler effect, but let's look at Doppler effect here. So it's an apparent change in the frequency of a sound because either the source or the receiver are moving, or both. Okay, so an apparent shift in the pitch, for example. So this is the source making noise, and this is the observer. So this one is not moving, so you hear the real pitch of the source. If it's moving toward you, the pitch will appear higher. Okay, so you have the wave front here being packed together more, and here, if you are located here, they are further apart from each other, so the pitch will be lower. And if the source moves at the speed of sound, you have a shock wave that will move. And when it's gonna cross you, it's gonna hurt, right? So it's called the Doppler effect. So you have two equations. You have two equations if the source is moving. Okay, so that will be the frequency that you hear. That will be the frequency of the source, that's the speed of the source, and that's the speed of sound. So that will be one equation. If the source is moving, and you can also have the case. So those slides come from Johnson and Cutnell that I recommend. And you also have the case when it's the observer moving. So if it's moving toward the source, you expect a higher pitch. Okay, so let's see the answer. So which one will cause the frequency to double? Okay, let's see. You should pause the video. So this one, you kind of need the equation. So the period is 34 milliseconds, and the frequency is 1 over the period. So if the frequency is multiplied by 2, then the period is divided by 2 because they are inversely proportional. So for example, number 3 is right. Okay, so it could be this one or that one. So then you have the choice between A and C. So sometimes you go for the easiest computation, and then you always keep in mind the multiple choices, right? So 3 only and 2. Let's see what 2 says. So in that case, the sound source is moving toward the observer. So the source is moving toward the observer. So that means it's this case moving toward, and we have an equation for that, right? So the equation is observer equals the source so okay, I didn't finish reading here. The source is moving toward the stationary observer at a speed equal to half the speed of sound, which is quite large. So here we have a 1, and here you have a 1 minus. That will be the speed of the source over the speed of sound. Let's check this equation here. Okay, and what do we have? We have that the source is 1/2 the speed of sound. So it's going to be Fs 1 minus. So here you're going to have a 1/2. Okay, so that means source, the frequency of the source, 1 over 1/2, which is 2. So this is also true. So between here and there, therefore, it's only 2 and 3. So this one could work as well, but they don't give us that choice, because if the observer was moving at the speed of sound, it's weird. Okay, that's not physically possible, because that means you will have a shock wave, right? If you move at the speed of sound, all those, from your perspective, all those wavefront will build up. Okay, so it will be shock wave. So that's why probably they don't have that as a solution. Okay, so again, you can pause the video. So this one is easy. Sometimes they have easy problem, which is nice. So you can try to do this one. So the speed of the wave on a string is 3 meters per second. And the wavelength is, so here you have to convert, right? So it's going to be 0.1 meters. What's the period? So we have the speed equals unit meter per second, so it should be a distance divided by a time. So which means 3 equals 0.1 divided by the period. So the period is 0.1 divided by 3. So you have 1/3, which is 0.333, and you divide by 10, so 0.03 second. The speed is also wavelength times the frequency, and the frequency is what over the period. So anyway, the answer is B. So this one is a nice one. So the next one, so here I found a typo. The answer does not seem to be here. It's a pipe with one end closed, or the third harmonic. So maybe you don't have to memorize the equation, but you see here it's closed, so we need a node, and here we have an antinode. So that's the idea of a clarinet. So that would be the first harmonic, the second harmonic, so it would be 1, 2, 3, so 3/4 of a wavelength. From here to there, it's 1/4 of a wavelength. And the third harmonic, you're going to have 5/4. So 1 and 2 and 3 and 4 and 5. Okay, so it will be 5/4 of a wavelength, which is given by this equation, but you don't need to memorize. You can make sense of those drawings. So first harmonic, second harmonic, third harmonic. Okay, so you know the wavelength will be 4/5L. And what is given? It's given that L equals 1.5, and you have the speed of the sound, and you want to find the frequency. So we want this one. So that will be for the third harmonic. So you have L, which is 1, 2, 3, 4, 5. So 5/4 of a wavelength, okay, which is 5/4. Wavelength is the speed of the wave over the frequency, right? So wavelength times frequency equals speed. So they are inversely proportional to each other, and I'm trying to find the frequency. So the frequency will be 5/4, the speed divided by L. And L is given is 1.5 meters, and V equals 340. So that's going to be equals to 5/4 times 340 times 3/2, 1.5, so that's going to be 2. So the frequency equals 5 times 340 over 2 times 3. So that will be in hertz. So if I want to put pi, okay, pi inside, we can say that omega equals 2 pi f. So the frequency will be equals to 5 times 340, 2 times 3 times 2 pi in rad per second. So you can cross that out. Maybe you can do this. So the frequency will be about 5 times 340. And that's hertz or rad. That will be rad per second, sorry. So anyway, that will be the answer. So if you want to keep if you want to keep the pi, it will be omega will be 5 times 340 over 2 times 3 times 2 pi. Okay, which is about, so omega will be 567 pi rad per second. So that will be the final answer. Okay, I will let you do the computation, but you see that for some reason it's not among the questions here. So that means it's wrong. So we go to the next question here, and this is the next question. So you can pause the video. So we measure the loudness of a sound as we hear it for human in decibels, right? That's because the human ears works on the log scale. So you have the intensity of a sound, which is in 1 per meter square. If the intensity increases by a step of 1, we cannot detect that. We can detect the change in intensity or the sound level only if the intensity is multiplied by a factor of 10, for example. Okay, it's multiplied by something. So that's how we have this relationship here. So that will be the intensity of sound relative to intensity of a reference, which sometimes is a threshold of hearing. And that here is what we call decibel, the decibel of sound. And that's because we work on a log scale. So that will be here the decibel. So if you increase the decibel by 10, the intensity is multiplied by 10. If you increase the decibel by 20, the intensity is multiplied by 100. If you increase here by 30, so a step of 30, from here to there, it will be multiplied by 1,000. Okay, you can check the math, but log of 10 is 1, log of 100 is 2, log of 1,000 is 3. Okay, so this is called the log scale. Okay, just if you take the log, a step of 1 means multiplied by 10, step of 2 multiplied by 100, step of 3 multiplied by 1,000. So that's how it works here. And there is the equation for that. But anyway, here they ask you is increased by 20 decibels. So if you have a increase of 20, so you can go from here to there. Okay, you don't have to start from here. So from here to there, there is a step of 10, 20. That means the intensity has been multiplied by 100. So the answer is C. And here it's a nice question, so you can. So here you have the last question you can do, and it's you can pause the video. It's a condition here. It's a real condition. You see that it's described there. Okay, so it means that the bones stuck in place. This is the little bones here. It doesn't move, so it doesn't transmit the sound anymore, right? Or it can transmit the sound, but it's very badly done. So what's going to happen if it cannot vibrate anymore, or vibrate a little, just a little bit, then, or if you can hear only from one ear, so obviously it's going to be a decrease in the perceived volume of sound. Pitch, no, because pitch, it depends how many wavelengths, it depends on the standing waves. So it has to be a decrease. It cannot be an increase, obviously. So that will be the only answer that will make sense. Okay, that's it for